I'm going to start with the code we had previously. Previously, we had these theta angle definitions, and they are in units of degrees, and then we convert the angles to radians. Previously, the next step that we did was calculate rotation matrices. This time, instead of calculating rotation matrices, the next thing I'm going to put here is the parameter table that we got from Denavit Hartenberg. For now, I'm just going to call it PT for parameter table. You can name this anything you want. We know that our parameter table is going to have 4 columns. And for now, I'm going to make it have 3 rows because we're going to use it to evaluate these examples that we just did. But you can use this same method to do any number of rows based upon the number of frames that you have or the number of degrees of freedom in your kinematic diagram. I don't want to put any particular parameter table in here yet. For now, I'm just going to make a placeholder. I'll put 0 in for each of these places, and we'll fill it in later on with the correct values. So here I've added my first row of the parameter table, and then I'll put a comma, and I'll enter a second row, then a third row, and we're done. Once we have the parameter table entered, we can use the parameter table to find each of the homogeneous transformation matrices. The thing that I want to type in here is this. This is the definition of the homogeneous transformation matrix when we're using the Denavit Hartenberg method. Let's type this in. In the upper left-hand corner, I have the cosine of theta 1. In my parameter table, theta 1 is the most upper left-hand corner. It's far to the left, and it's the first row. In Python, here's how I can type in the cosine of my previous parameter table element. I'll do np.cos of pt row 0, column 0. In Python, matrices are numbered with the first row being row 0 and the first column being column 0. The second element in my homogeneous transformation matrix is the negative sign of theta n, which as we know is pt, the first row and the first column, times the cosine of alpha. Alpha of the first row is my parameter table, the first row, but the second column. The next element of the homogeneous transformation matrix is the sine of theta times the sine of alpha. We're still using the first row because this is our first homogeneous transformation matrix, but now we're going to use the second column because alpha shows up in our second column of the parameter table. The last element of the first row of the homogeneous transformation matrix is Rn times cosine of theta n. Rn shows up in the third column of our parameter table. So we'll do pt, the first row, but the third column. Remember that the third column will be accessed with the number 2 since the first column is column number 0. Times the cosine of theta, the first row and the first column. We've now finished the first row of our homogeneous transformation table. I want to continue entering this matrix on the next line just to make it look a little nicer. So I'll type a comma here to indicate that we're going on to the next row of the matrix, and then I'll hit enter and we'll start the new row here. In row 2, the first element is the sine of theta. The second element is the cosine of theta times the cosine of alpha. Alpha is in the second column, so I put a 1 in the second index of this reference. The third element is negative cosine of theta times the sine of alpha. Alpha 1 shows up in the first row and the second column. And lastly, we have Rn times the sine of theta n. Rn is, we're still in the first row, but it's in column 2, or the third column, which is accessed with the number 2. Times the sine of theta in the first row. Then I'll end this row of the matrix, put a comma to indicate we're moving on to the next row. Now, in row 3, we have a 0, and then the sine of alpha, still in the first row, alpha's in the second column. Then we have the cosine of alpha, and then we have d. D can be found in our parameter table, still on the same row, but in the fourth column, which is accessed with number 3. Finally, we're on to the fourth row of the homogeneous transformation matrix. The fourth row is simple. It's 0, 0, 0, 1. And we're done with the whole matrix. Now, let's go back up to the parameter table and fill in one of the parameter tables that we derived. Let's start with the Cartesian manipulator table. When we found the table for the Cartesian manipulator, we had the first row was 90, 90, 0, and then A1 plus D1. Before we go any further, let's make some fixes here. First of all, these 90 values are in degrees, but we need to get them into radians. I'm just going to do the conversion right here. We divide by 180. Make sure you put the point 0 here so that we do a floating point calculation instead of an integer calculation. And we want to multiply by pi. Let's do the same thing with the next one. Now, in this fourth element, we have A1 plus D1. We haven't anywhere specified what these values are. We've only put in theta for our joint variables, and we haven't put any link lengths in at all. Let's add some variables that we can use for displacement values and also some link lengths. For now, I'm going to set all of these things equal to 1. Okay, let's correctly put in the second row of our parameter table. I'm going to put this on to the next line so it's a little bit easier to see. The next row of our parameter table that we found for the Cartesian manipulator was 90, negative 90, 0, A2 plus D2. I'm going to copy this calculation of 90, paste it here also, and then change this to negative. And then we have 0, and then the fourth element was A2 plus D2. The third row was 0, 0, 0, A3 plus D3. Let's take everything that comes after H01 and comment it out. So you might not have the exact same code as me here, that's fine. Take whatever you have, and for now, click on the Format menu, and then 3 elements down there's something that says Comment Out Region. Click on that and it will add comments to everything else so that nothing else will run other than these lines. Now let's do print H01 and let's run this. The matrix output is really hard to see, so let's change how we're displaying it. We'll use np.matrix. Now let's think for a minute about what this matrix means so that we can do some debugging and see whether we've done our work correctly. This upper left-hand corner 3 by 3 matrix is the rotation matrix. And this matrix that has been calculated for us says it's 0, 1, 0, 0, 0, 1, 1, 0, 0. This is telling us that in frame 1, the x-axis is in the same direction as the y0 axis. We want to look at our kinematic diagram and make sure that that's correct. It also says that our y1 axis is in the same direction as z0. In our kinematic diagram, that also looks correct. And the z1 axis is in the same direction as x0. That's also correct in our diagram. So far, it looks like we're doing okay. Also, this 3 by 1 vector at the end tells us the position of the center of frame 1 relative to frame 0. Here it says that the displacement between these two frames is 0 in the x0 direction, 0 in the y0 direction, and 2 in the z0 direction. That makes sense since we put into our code that A1 is equal to 1 and D1 is also equal to 1. Everything looks good so far. Let's go back to our code and put in the other matrices, H12 and H23. Copy H01 and then paste it. We'll change this name to H12. Now the only thing that needs to change here is that instead of accessing the first row, we want to access the second row of our parameter table. So all we need to do is change these zeros to ones. Now instead of doing that, I'm going to do it a little bit differently to make this work better for different numbers of degrees of freedom. Instead of changing this first number from 0 to 1, I'm going to change it to I. Okay, now before this matrix, I'll set I equal to 1. I'm actually going to copy this and I'll replace what we did previously, like this. I'll set I equal to 0 and then I'll call this 0, 1. The reason that I want to do this is because I'm trying to take you through one step at a time how we might automate the calculation of homogeneous transformation matrices in the future. We could put this matrix calculation in a loop to calculate as many degrees of freedom as we might have in our manipulator. Let's calculate the third matrix also. I'll copy this and paste it. Set I equal to 2, and this will be the matrix 2, 3. Now, let's print out each one of our 3 matrices. I actually wanted this other one to be after. Let me put this. There we go, one at a time. And I'm also going to put in a line to print something to let me know which matrix is which. Let's do print H0, 1 equals and we'll do the same thing for 2, 3. And then lastly, let's calculate H03. We'll first calculate H02 by dotting together H01 and H12. And then we'll calculate H03 by dotting together H02 and H23. And we'll print the final result. Okay, let's run this. Let's look at H03 and see if this matrix makes sense. This matrix is telling us that our x3 axis is in the same direction as z0. That appears to be true from our kinematic diagram. It says that y3 is in the opposite direction as x0. That's also true in our diagram. It says that z3 is in the opposite direction as y0, and that also is true in our diagram. Finally, our matrix is telling us that the position of the center of the last frame, that is the position of our end effector, is equal to 2 units in the x0 direction, negative 2 units in the y0 direction, and positive 2 units in the z0 direction. That appears to be correct from our diagram, remembering that we set each link length to 1 and each displacement value also to 1. You can now use this same method to check our other parameter tables. The only thing you need to change to check another parameter table is this, the parameter table. Everything after that, the homogeneous transformation matrices, the multiplication, and so on, will be the same regardless of the manipulator. Try doing at least one of these on your own. Take one of the other parameter tables that we calculated in the examples and put the parameter table into this code and run it. Check and make sure that the homogeneous transformation matrix looks right by looking at the position of the end effector and also the rotation matrix, which should be telling you how the end effector frame is rotated relative to the base frame.